Hi everyone. So today we're going to talk about absolute value functions. And if you consider a function y equals f of x, the absolute value function would be y equals absolute value of f of x. So what we're going to do to start, just to sort of investigate, is to look at a few absolute value functions in action. And so I'm going to ask you guys to graph these on your calculator. And I don't have a graphing calculator on my iPad. So what I did was I took screenshots of the graphs of these, which I'm going to show you in a moment. Okay, so we've got 4 examples. The A and B are linear functions. Okay, where the original function is linear. And C and D are where the original functions are quadratic. Okay, and so we're going to sort of graph these one at a time and just see what happens. Now, just so that you know where to find absolute value on the TI calculators, I'll write this over here maybe. And to be honest, I can't remember off the top of my head where they are on the Casio, but I will find out. And then when we talk in class, I will tell you exactly where to find that button. You go to the math button, which is kind of just a couple below the second button. And then you go over to the right where it says num, N-U-M. And then you hit number 1 for absolute value. And it'll open up a bracket. And then whatever you put in the brackets, you have to close the brackets at the end, the graphing calculator will take the absolute value of that. Okay, so if you want to enter in an absolute value on your calculator, that's how you would do it. Okay, so the first one that we're going to look at is the absolute value, or y equals 2x plus 5, and y equals the absolute value of 2x plus 5. So I'll show you the picture of that. That one is, oh no, that's not this one. That's this one. Okay, so you can see y equals 2x plus 5. I'm not going to be able to write on here, but the y-intercept is 5, and the slope is 2 over 1, 2 over 1. So that's the blue graph that starts in the third quadrant, and then it kind of continues and becomes the red graph. Okay, the second function is the red one. Okay, so for part of it, it's the exact same as y equals 2x plus 5. But for the other part, it kind of flips over the x-axis. Okay, so what we're going to do is just draw a little picture of that. Now it looks like the y-intercept is 5 and the x-intercept is negative 2.5. So I'm going to draw a sketch of that in our notes. Okay, so this is A, and it looks like this. Here's 5, here's negative 2.5, and this was the first graph. Okay, and then I'm going to do this in a different color. Maybe I'll do it in blue. The second graph looked like this. So for this part, it was kind of overlapping. But then over here, it reflected in the x-axis. Okay, so that was number 1, or A, I should say. All right. Okay, let's look at B. So B was y equals negative 4x plus 3. And the absolute y equals the absolute value of negative 4x plus 3. And when I graphed both of those, I saw this. Okay, so similar sort of thing. The blue graph is the y equals negative 4x plus 3. So it's kind of in the fourth quadrant, but then it overlaps with the red graph as well. So for part of the graph, the two of them are overlapping. And then for the other part, one of them is a reflection of the other. Okay, so the blue graph and the red graph is a straight line. And then the absolute value graph is like a V. Okay, and it looks here like one intercept is at 3 and the other one is at about 2/3 or so. So let's just draw that one in. Okay, so this is B. So here's 3, here's 2/3, and the one graph looks like this. You can see the slope is negative. And then the other one is overlapping for part of it. And then it reflects in the x-axis for the other half. Okay. All right, let's look at the quadratic ones. So the first one is y equals x squared plus 4x minus 6. And the second one is the absolute value of that function. So I'm going to pull those up as well. And let me just find it. That one is this guy over here. Okay, so you can see, and in fact, it's not, you can see actually the vertex is at this point down here, whoops, which is -2, -10. And then the sort of, when you reflect it, that same point in the absolute value function is at -2, 10, right? So the same sort of thing happens. You get this parabola where the blue/red one is the original function and part of it overlaps with the absolute value and part of it doesn't. Okay, so let's just draw a little diagram of that. Oh, and the zeros, it's hard to tell. It looks like the zeros are irrational. So we'll just do our best to sort of imitate what we saw there. So this is C. And let's see, well, we know what the vertex was. The vertex was at -2, -10. And there's a point there. And then it kind of went like this. That was the original. And this was the absolute value function. So for this part, it overlapped. Oh, that's good. I think I did the highlighter there or something. I don't know. There we go. Okay. And then this reflected. So this point over here is -2, 10. Okay. So that's C. And then the last one is y equals -x squared plus x plus 1, and y equals the absolute value of that. So we'll go back to the pictures, and that is this one. Okay, so again, the blue one is the original, and it turns into the red, then it turns back into the blue, and the red one is the absolute value function. Okay, so, and actually, wait, hold on. Let me just look at more details about that. So it's hard to kind of tell. The zeros, it looks like, are irrational again, and the vertex looks like it's just below 1 for the x value, just above 1 for the y value, roughly. So I don't know, we'll do a rough sketch. Anyway, we'll do our best. Okay, but it looked, vertex is about here. And there's the original. Okay, and then the absolute value function overlapped here. That was the overlapping part. But then it reflected here. Okay. So that was the absolute value function. Now, what you may have noticed is that the overlapping parts of these two functions are always where the original function was positive. And the reflected parts are where the original function was negative. And the reason for that is that the absolute value makes negative values positive. So whenever you have a negative value in the original, let's say we're looking at this one, and you're looking at this point on the original right here, which is a negative value. When I take the absolute value of that, it's going to make it positive. Okay, or here, if I have a negative value here, okay, in the original, and then I take the absolute value of that, well, the absolute value is going to make that value positive. So I'm going to reflect anything that's negative in the original function in the x-axis. And that is exactly how we graph these absolute value functions. Okay, now some points are the same, right? So firstly, there's these overlapping points, and then the x-intercepts are where they sort of start to diverge from one another. Okay, and that's because that's where the function is equal to 0, right? So the absolute value of 0 is 0. And then the function, the original function, is either going to be positive or negative once it's 0, like it's going to go in one or two directions. And so that's where it will start to either overlap or reflect from the original in terms of the absolute value function. Okay, so those x-intercepts, there's a couple notes that I want to make. I'm just not sure where I'm going to have room to make them. Let's see, I'll try and make them here. Now I don't know why. Let's see if I can change that. Oh, I have to use this, that's why. I think I was using like a transparent pencil. Okay, notes. Number 1, the x-intercepts always stay the same. Okay, and they are called, we've heard this term before, invariant points. Okay, so we saw that come up when we looked at reciprocal functions. Okay, so the other thing, number 2, is if the original function is positive, the absolute value function will just overlap with it. Or you can think of it as above the x-axis. The absolute value function will overlap. Okay. But if the original function is negative, or below the axis, or below the x-axis, the absolute value function will reflect in the x-axis. Okay, now here, this is where we talk about something called a piecewise function. And a piecewise function is essentially when you take a function that's comprised of several parts and you piece them all together. So for example, you might say that f of x equals x if x is greater than 0, or 5 is if x is less than 0, right? That's an example of a piecewise function. If you were to talk about that, right? So for example, you could say that f of x equals x if x is greater than or equal to 0, and 5 if x is less than 0. This is just a simple example of a piecewise function. Now, what would this look like? Well, if x is greater than 0, the graph looks like y equals x, which is like this. If x is less than 0, the graph looks like 5, which is like this. That's an example of a piecewise function. Okay? And essentially, it's called a piecewise function because we can't express this function as a single function. We have to split it up into two parts. We can't use a single equation to write out this function, right? Because it's kind of divided into two sections. Okay? Now, that is also true for absolute value functions. Okay? Essentially, if we wanted to remove the absolute value symbols from a function, we would say this. If y equals the absolute value of f of x, then y equals the following. If f of x is positive, then y is just the same as f of x, right? Because they overlap. So y equals f of x if f of x is greater than or equal to 0. So anytime f of x is positive or greater than or equal to 0, the function is exactly the same. Or y equals negative f of x if f of x is less than 0. Now, why is it negative f of x? Well, if f of x is less than 0, f of x is already a negative number. If you put a negative sign in front of that, let's say f of x is negative 5, okay? If I put a negative sign in front of negative 5, now it becomes negative negative 5. Now it's positive, okay? So this makes it positive. Because now, since f of x is negative in the first place, if you stick an extra negative sign in front of it, you've got two negative signs, that makes it positive. Okay, so now we've essentially expressed the absolute value function as a piecewise function. Okay, and we're going to practice doing this. All right, so let's do a couple of examples. Okay, so for the following functions, A, determine the x and y intercepts, B, sketch the graph, C, state the domain and range, and D, expresses a piecewise function. So what I always recommend with these functions, when you're doing absolute value functions, is picture the original function first. Okay, so you want to think of what does y equals 3x plus 1 look like? Okay. Right, so what does y equals 3x plus 1 look like? Well, and in fact, we don't necessarily have to go in that order. We could start out by saying, okay, well, the y-intercept here equals 1, because it's like y equals mx plus b, right? And the y-intercept equals 1 also because the y-intercept is whatever y is when x equals 0, right? So plug in x equals 0. That's because y equals the absolute value of 3 times 0 plus 1, which is 1. Right? So this is our y-intercept. For our x-intercept, now y is equal to 0, right? So this is our y-intercept. For our x-intercept, x equals 0. So if I plug as a 0 in for y, I'm going to get 0 equals the absolute value of 3x plus 1. Okay? Well, if an absolute value equals 0, then whatever's inside the absolute value also has to equal 0. That's the only way you're going to get 0. So this is going to be 0 equals 3x plus 1, which means negative 1 equals 3x, which means that x equals negative 1/3. Okay, so this is our X-intercept. It's also going to be the invariant point. Okay, so this is sort of step A, are your intercepts. Now step B, sketch a graph. This is I was kind of going in out of order here, but this is where I would really encourage you guys to picture the original. And I'm actually going to do this, that's kind of the see-through one, using a different color. So if I were to graph y equals 3x plus 1, okay, my y-intercept would be at 1, and then I'd go up 3 and right 1. So my next point would be there, or I could go down 3 and left 1, right? So this would be the original function. Okay, so this is y equals 3x plus 1. What we want to graph, though, is the absolute value of that. So what we know is that wherever f of x equals 0, is greater than 0, they overlap. So here's where is positive. Oh, I'm going to switch to okay, so here is where everything's positive. So here they're just going to overlap. Where the original function is less than 0, it's going to reflect in the x-axis. So this is going to look like this. Okay, and this is this function. So there's our graph. Okay, now if we look at the domain, this is part C. Domain, well, if you look at your arrows, this arrow over here that I'm kind of clicking on, that one's in the horizontal direction going right. This arrow over here is going left. So for our domain, x is an element of the real numbers. You can also write it as negative infinity to infinity if you want. For your range, though, well, y can only be greater than or equal to 0, right? Because there's this minimum point down here. So for our range, y is greater than or equal to 0. You could also write this way. Okay. And then finally, D. Well, remember, expressed as a piecewise function, y equals f of x if f of x is greater than or equal to 0, and negative f of x if f of x is less than 0. So we have to figure out where is the point where f of x is equal to 0, and that's right here when x is negative 1/3. Okay, so in terms of the piecewise function, y is going to equal the original function, which is 3x plus 1, whenever x is greater than or equal to negative 1/3. Sorry, negative 1/3. And x is going to equal the negative of that, negative 3x plus 1, if x is less than negative 1/3. Okay, so this is part D. Okay, all right, so that's one question. And we're going to do one more, and then we're going to be done for today. Okay, so here's the next one. Okay, so the first thing we have been asked to find is the x and the y-intercept. Okay, so for the y-intercept, x is 0. So I'm just going to plug in a 0 for x, and I'm going to get y equals the absolute value of 0 squared minus 0 minus 2, which is the absolute value of negative 2, which is 2. So that's my y-intercept. For the x-intercept, y equals 0. Okay, so I'm going to get 0 equals the absolute value of x squared minus x minus 2. And if the absolute value equals 0, then whatever's inside the absolute value equals 0. So I can remove those absolute value symbols. And now I have to factor. And I'm looking for two numbers that multiply to -2 and add to -1. And those two numbers are x minus 2 and x plus 1. And so I get that x equals 2 and -1. Okay. So now, based on this, I can start to graph this thing. Okay. Now, when I'm graphing this, I want to kind of picture the original to start. Okay. So I am going to, again, just do that in a different, well, actually, I'll set up my axes first. Okay, so this is part B. Do that first. So I've got, let's see, I've got a 0 at -1 and at 2. Okay, and if this was a parabola, this would open upwards. So you can imagine that this would kind of go like this. Oh, I was going to do this in a different color. Sorry, let me change that. I'll do my absolute value function in black because that's what I was actually asked to graph. Okay, so here we go. Okay, so if we actually have the original function, right, the two zeros would be at -1 and 2. This parabola would open up because the value of a is 1. So this would kind of look like this. And the y-intercept would be here at -2, right? Because the y-intercept of the absolute value function is at 2. Now, for the absolute value function, we know that whenever the original function is positive, they're going to overlap. So that would be here. Oh, let me actually switch to the solid here. And here. Okay. And then this y-intercept was at 2. And this part that's below is going to reflect. So it's going to go like that. Okay, so that's part B. Now for part C, domain and range. So again, we've got an arrow going left and an arrow going right. So for the domain, X is an element of the reals. And for the range, we have a lowest point, right? In fact, there's two of them, right here and here. And those are both when y equals 0. So our range is y is greater than or equal to 0. Okay, and then finally the piecewise function. So we have to figure out when is the function, the original function, greater than or equal to 0. And that's in two regions, right? The original function is greater than or equal to 0, essentially here and here, right? Now, where is it less than or equal to 0? It's less than or equal to 0 here to here. Not less than or equal to, sorry, just less than 0 here to here. Okay, so I have to essentially put that into a piecewise function. So for part D, y is going to equal the original function, which is x squared minus x minus 2, if x is either greater than, or sorry, I should go from smallest to largest, less than -1, or equal to -1, I should say, or x is greater than or equal to 2, and x is equal to negative of that function, x squared minus x minus 2, if x is between -1 and 2 exclusive. So actually, I'll do that as a double inequality. We'll do it this way. if -1 is less than x is less than 2. Okay, so that is how you would write out the piecewise function. All right, so I am going to end here for today, and I will see you guys tomorrow, and we will talk about absolute value equations.